The foot of a 5-meter ladder leaning against a tall wall is being pulled away from the wall at the rate of 2 meters per second. At what rate is the ladder rotating when its foot is A, 3 meters from the wall, or B, 4 meters from the wall? So, a couple important things. The wall is tall so that we cannot end up having to worry about the ladder overlapping on it. So we'll have the ground, and we have a tall wall, and then we have a ladder. And what we know is the ladder does not overhang the wall because it's, quote, tall. So the foot of a 5-meter long ladder, I'm going to call the length of the ladder S. Is leaning against a tall wall, being pulled away from the wall at the rate of 2 meters per second. So the foot is being pulled out at 2 meters per second. We need to name our other things, so I'm going to name the distance from the wall x, and I'm going to name the height of the wall h. We want to know at what rate is the ladder rotating, which means what's the change in the angle. They don't name an angle, so I'm going to choose that as my angle theta. And we'd like to know how fast that is rotating at a certain point. So for related rates problems, and this is clearly related rates because we have an at rate thing in it, what we want to know is we want to say what is given as constant, what is desired, and when do we want to know it? When is it desired? Usually the when is it desired is going to be more of a condition than a time, but depends on the problem. So what's given as constant? Well, we know that the ladder is always 5 meters. And we know that the ladder is being pulled away at a fixed rate, and that's going to be dx dt, which grows at 2 meters per second. What we're looking for is d theta dt. And then when do we want it? Ends up depending in part A, it's when x is 3, and part B is when x equals 4. We're going to find those two are really basically the same, just different numbers. After identifying those things, our next step is to try and connect the quantities that we have into the quantities that we want. We want to relate theta to x so that we can relate d theta dt to dx dt. So we look geometrically and we say, oh, well, the cosine of theta is x over s. Or we can say that x is s cosine theta. And that's going to allow us to take the derivative pretty easily so as to get the rates that we want. We want to take a time derivative of the entire equation. On the left, that will yield dx dt. On the right, s is a constant, so it comes out front. And the derivative of cosine is minus the sine of theta. But we weren't taking the derivative with respect to theta, we were doing it with respect to time, so we also pick up a d theta dt. This allows us to solve it over for d theta dt, which is clearly going to be just dx dt over minus s sine of theta. My management of the page has not been particularly great, so we'd actually have to go to a different page just to see what comes out, but it's pretty easy from here on out. So we have, to remind you, d theta dt is dx dt over, I have a minus sign which I'm going to put out front, s sine theta. When x equals 3, then pretty clearly we have h equals 4 because s equals 5 and it's a Pythagorean triplet, and therefore the sine of theta, which will be h over s, will be 4 over 5, and therefore d theta dt will be minus 2 over 5 times 4/5, all of which ends up being just minus 1/2. In exactly the same way, and of course by conveniently chosen values of x and s, when x equals 4, then h equals 3. It's the other way of doing it, and therefore sine of theta is, well, still of course going to be h over s, so now it's going to be 3 over 5, and therefore d theta dt is minus the same factor of 2 over 5 times 3/5, which gives us minus 2/3. And those are the two rates in obviously radians per second.